we define a set S with 4 elements 1, 2, 3, 4. From this set, we choose 4 elements and enumerate all permutations. Test permutation. This set S has 4 elements. We select 4 elements out of a set with 4 elements. Stream and there. Now we try another one. From a set S with 4 elements, we choose 3 elements and enumerate all permutations. Test permutations for 3. I will copy this and paste it here. Start command prompt. We will build CLS A. So from the set S 1, 2, 3, 4 elements, we generate all permutations 1, 2, 3, 4, 1, 2, 4, 3, and lastly 4, 3, 2, 1. In this case, out of the set with 4 elements, we select 3 elements and we make permutations like this. Hi everyone, my name is Thomas Kim. Today is July 4th, 2019. This is my 46th episode about the future of C++ programming, C++ 2A standard. In this episode, I will talk about problem solving strategy. Einstein said that everything should be made as simple as possible, but not simpler. Albert Einstein said that everything should be made as simple as possible, but not simpler. I would say the worst algorithm is better than no algorithm. There can be poor algorithm, but there is no worst algorithm. When we first attack a new problem, always try to make it done. You can use whatever resource you have to solve the problem at hand. Only after solving your problem, you can improve it later. In this episode, we will enumerate permutations with the simplest method that I know of. Then we can improve its performance later. As I said in our previous episode, our problem solving strategy. First off, understand your problem crystal clear. Second, use the simplest approach to solve the problem. In my case, I usually use recursion 9 out of 10 cases. Recursion is the term used by programmers. Those mathematicians use fancy words such as mathematical induction. Once you implement the algorithm, then you can improve your algorithm later when you gain more insight and experience. In arithmetic, once you learn addition and multiplication, subtraction and division comes free. In the same manner, once you learn enumeration of subsets, enumeration of permutation comes almost free. With the enumeration of subsets or combinations and the enumeration of permutations, you can enumerate almost anything. If you haven't watched my previous episode, Turning Mathematics into C++ Algorithm, episode 45, please click this link and please watch this video, then come back to current session. If you understand my previous episode, then my current session will be just a piece of cake. Okay, let's get started. On the CPP extension folder, please click Tutorial folder. Click this button, 046 Permutations.cpp. Hit enter. Ctrl V, Ctrl plus, include talkplay fun, output HPP, include talkplay fun, ncr npr.hpp, talkplay fun, ss stream, auto, and l, talkplay fun, and l, auto, and l, talkplay fun, and l. Please note that this is one carriage return and flush to console output. Two carriage return and flush to console output. Void build permutation using element t, size t, using set t. We can use vector std, vector element t, set t s, set t r, it should be reference, size tr, size t ems, void test permutation, size tn, size tr, set t s n, allocate memory for n elements, std, iota, s, begin, s, end, we will put it 0, initial value 0, string, the set s, and int main. I will copy this function, for start command prompt. You should be in CPP extension tutorial folder, dir 046 star. So we are compiling this file, cl ehsc std c++17 046 permutations.cpp fe aexe, hit enter, cls. Now it works. Now I need to explain some theories behind. In our previous episode, we learned from a set S 1, 2, 3, 4. We used Pascal's triangle like this. NCR equals n-1 c r-1 plus n-1 C, R. Please note that from a set with n elements, we reduced the set to n-1 elements. That is, from a set S, 1, 2, 3, 4 elements, we reduced the problem to S prime, 2, 3, 4, and we stashed the first element here. We reduced the problem from n to n-1. This is the key. If your problem is complex, reduce your domain from n to n-1, or sometimes n to n-2. You can solve most of your problem by reducing from n to n-1, or sometimes this does not work. Then try to reduce from n to n-2. Okay? If it works, then you can prefer this one because it's faster. If it does not work, then try to find this solution. This technique is what I want to teach you. Some of you, the sagacious, may already understand what I am going to do. Here, we have a set of 4 elements. We have initially a set with 4 elements, 1, 2, 3, 4. We reduce this problem S prime, 2, 3, 4. In this case, we stashed number 1 first element, or 1, 3, 4. We stashed 2, or 1, 2, 4. We stashed number 3, or 1, 2, 3. We stashed number 4. So from this set with 4 elements, we reduce to set with 3 elements, like this. That is, we are reducing from n to n-1. This is the key. Now, in this case, the set S has 4 elements. We are choosing 3 elements. Okay? Then we enumerate permutation. That is, n is 4, R is 3. Okay, because we are choosing 3 elements. Here, mth starts from 0 and ends with 23. So, mth is greater than or equal to 0 and less than 4 permutation 3. This number is 24. Now let's think about this number 1, 2, 3, 4. Okay? This part, the count of this number, we take out 1, then we have 3 elements, 2, 3, 4. From 3, we are going to select 3 in total. Since we already selected 1, in this case, we select 2. Okay? If we select 2, in this case, in this range, then we have 1, 3, 4. So we have 3 elements left. Then if we selected 2 already, we select 2 more. In this case, we select 3. Then we have 3 numbers left. From 3 numbers, we select 2 more because we select 2 more. This is the same. Okay? If we select from set S with 4 elements, we select 4, then we are left 1, 2, 3, 3 elements. 3, P, 2. Let's see once again. From the set S, we select 1, then we are left 2, 3, 4. Since we already selected 1, from this set, we select 2 more. So 3, 2 more. Okay? In this case, if we select 2, from original set S, if we select 2, then we are left 1, 3, 4. Since we already selected 2, we can select from the set with 3 elements, we can select 2 more. Okay? In the same manner, here, if we select 3 from set S, for example, we selected 3, then we have 1, 2, 4. 1, 2, 4. From this set, we select 2 more. Okay? Also from this set, original set, we select 4. Then we are left 1, 2, 3. From this set, we select 2 more. From the set with 3 elements, we select 2 more. How many these? 1, 2, 3, 4. So N, P, R, N times N minus 1, P, R minus 1. For example, we are computing 4, P, 3, 4, P, 3 equals 4 times 3, P, 2. what you should learn is that we reduced from 4p3 to 3p2 or n to n minus 1. Remembering this point is the highlight of this episode. Remembering this technique is really important. If you remember this technique, you can solve any problem. If you remember this, you can solve any problem. I am not lying. I am not exaggerating. If you remember this, you can solve any problem. Suppose we are given a function build permute and we have parameter s here and r the result set and r and m's like this given, and this count n can be determined as size is n, and we have r and m's can be a value greater than or equal to 0, less than n p r. Okay, so this value is given, this value is given, and this value is given. Since n and r is given, npr is given. Okay, how can you decide this number, this number, this number, and this number? Please note that this, and this is determined by n-1 p r-1. Okay, also this count m-1 p r-1, and this count n-1 p r-1, and this count m-1 p r-1. Okay, in this case n is 4. The number of elements of set S is 4, and we choose 3 elements, so initially R is 3. This value becomes 4 permutations 3, so it becomes 24. Okay, I said m's is given, and this becomes 3p2. We learned this equation, 4p3 equals 4 times 3p2. So when MC is given, for example, if MC is, let's see, 7, for example, MC is 7, then we compute quotient like this. Quotient equals m's divide n-1 p r-1, so 7 divide by 3 p 2 7. This number is 1 2 3 4 5 6. This number is 6. The quotient is 1. Okay, so we selected the quotient 1. This 1 means this is 0, 1, 2, 3. So it means number 2. This is index. Okay, so we can select 2 like this. R is this set. We push back, we insert from this set S quotient like this. Okay, we push, quotient is 1, this value is 1, so it becomes R push back S1, and this value is 2. So we are putting 2. Then R becomes 2. Okay? Now we compute m's again. New m's. New m's becomes m's. This is all the m's. Modulo. This is remainder. n-1 p r-1. Okay? This is new m's. Initially m's was 7. Modulo. This value is 6. The remainder is 1. Okay? So new m's becomes 1. And S prime, all the S, we remove this value. So 1, 3, 4. Okay? Now we defined everything. So we call this build function again. Build permu. We put S prime. We put R. Now we selected one element, so we minus 1. R minus 1, because we already have chosen this number. And m's, new m's. So we are calling this function recursively. So you have to understand this equation. 1. You have to understand this equation, and you have to understand this equation 2, and you have to understand this equation 3, and you have to understand this operation 4, and you have to understand this operation 5, and we call 5, then we call this function recursively. So this is 6. Now let's see in code. We will start with the test permutation function first. Here, auto max mth top plate fun NCR NPR NPR N R. We got N R as function parameter. We compute max m's NPR for size t m's equals 0, m's less than max m's plus m's. Okay, we are in a loop. Set t r. We declare r here. Now we call this function s. We initialized s here, and we provide r, then r, then m's, then stream m's, then we print out r. This is permutation. We print out r, then end line like this. Now I will give some spacing. Set w. We will put 3. Now here, if r is 0 or s empty, we simply return auto n-1 p r-1 auto n equals s size. So here talk play fun NCR NPR NPR n-1 r-1. Okay, we computed this value. Then auto quotient m's divide n-1 p r-1. This is use index of s. Okay, then r pushback S quotient. Okay, then we have to remove this element, insert quotient element of S to R. Then we delete from S, erase S, begin plus quotient. Remove S quotient from S. Now we compute M's. M's modulo N-1 P R-1. Okay? It can be represented like this. Like this. Okay? This is the same to M's equals M's modulo N1 P R minus 1. Now at this point we prepared S. This is S prime. This is S prime. Okay? For example, 1, 3, 4. If n is 4, then it becomes n is 4, r is 3, then it becomes 3 p2, and this value becomes 7 divided by, and this value is 6. 7 divided by 6 becomes 1. Or 1, like this. Then originally S was 1, 2, 3, 4, and we remove this element, 0, 1, 2, 3, so we remove this is quotient. Okay, index, we remove first element because it is 1. Then if we remove this element, then we have 1, 3, 4. This is S prime. Okay? And in this case, 7 modulo 6. So M's becomes 1. Remainder. Now we are calling this function recursively. Like this. S R R minus 1 M's. Okay? We are calling recursively. Now let's try on the command prompt. We build again CLS A. So from a set 1, 2, 3, 4, we are enumerating 4 elements like this. Now here string and the line. Now we select 3, 2, 1, if 0, like this. Now let's try it. CLS. So initially from 4 elements we select 4 elements, so 24 permutations. Now we select 3 elements from 0 to 24 elements, 24 permutations. Now we select 2 elements 0 to 12. Okay, now we select 1, 0, 1, 2, 3, 0, 1, 2, 3, 4. Now we select no elements, then it is empty. So all permutation works properly. I will post complete source code to my website, extension talkplayfun.com website. By the time you watch this video, if you click this link, you can download the complete source code. If you download the source code, unzip it, then in CPP extension tutorial folder, you can find the source code of this episode. Please subscribe to my YouTube channel. Thank you for watching.